This meeting is being recorded.
Hi everyone, welcome to our 38th session of the MedAI Group Exchange. This week we have Karan Singhal from Google Research here with us to present the work on generalization and personalization in federated learning. Karan leads a team of engineers and researchers at Google Research, working on representation learning and federated learning with applications in medical AI. He is broadly interested in developing and validating techniques that lead to wider adoption of AI that benefits people. Prior to joining Google, he received an MS and BS in computer science from Stanford University. Thank you, Karan, for joining us today. Could you please let us know your preference on how you want to take questions?
Yeah, people can feel free to kind of jump in with questions throughout the talk, and I'll hopefully have a little bit of time at the end of the talk for questions as well.
All right, sounds good. Let's try to make this session as interactive as possible with good audience participation. Without further ado, let me hand it over to Karan.
Cool, thank you. Yeah, so I'm Karan. I'm leading a team at Google Research focusing on representation learning and federated learning. So I wanted to talk about two of our recent papers and how they have connections to medical AI. And yeah, like I said, feel free to kind of jump in anytime with questions. I mean, for this to be a little bit more of a discussion than a lecture. Cool. So I will not assume any kind of familiarity with federated learning. So I'll kind of start by giving an overview of federated learning. Then I'll talk more about generalization of federated learning and what that means. Next, I'll talk about generalization in medical AI and what that previous content had to do with medical AI. And lastly, I'll talk about federated reconstruction, which is a way of improving generalization in contexts like medical AI. So let me start by giving an overview of federated learning. So for those unfamiliar, federated learning is a machine learning setting where clients like mobile devices or organizations like hospitals, for example, can collaboratively train a model via communication with a central server without actually sharing their raw data. So an example is a bunch of hospitals want to kind of collaborate to train an X-ray classifier without sharing the raw data of the X-rays that they have. Feel free to stop me anytime if anything is unclear. So to get a little bit more detail into federated learning, typically what you have on the left side is you have client devices. So in this picture, it's potentially mobile phones, but it can be also devices stored in a hospital, for example. They participate in federated training with a central server. The central server doesn't see any of the raw data, but coordinates kind of the activities of federated learning. A model development engineer might kind of coordinate the federated training so that it results in a model. And the end result is one or potentially multiple models that can be deployed to the end devices that we care about. So typically in federated learning, you learn a single model that aims to perform well on all clients' data. That's a typical setting. And the most common baseline algorithm is federated averaging. So let me kind of go through that a little bit so you guys have a little bit more color on what that looks like. So typically you have a server and you have devices. So as a reminder, the devices can be any kind of devices, either like mobile phones, potentially medical data, or hospitals with their own data that they don't want to kind of share with the public. So typically what you do is randomly select a subset of clients. You would send the latest weights from the server to those clients. So at the beginning of training, you would just randomly initialize those weights. Later in training, those weights are trained. Next, you update those weights locally using one or more steps of SGD, stochastic gradient descent. So each of the devices with their own local data only updates the model by performing SGD, and then they compute a delta, which is a difference between the initial model and their final model. Does that make sense? Cool. And then these deltas are aggregated across clients on the server. So a very typical thing to do here is average them, and that's what is typically done in federated averaging. And then that average delta is used to update the global weights for the next round. So the W is now updated. And so now we repeat the process over and over again. The server again sends out the updated W to clients. They compute local updates, and then that's all aggregated again. So basically by repeating this over hundreds or thousands of rounds, you can basically train a final model.
Quick question here, Karan. Do you, like in this setting, do each of the devices have their own validation sets as well, where they're computing the losses, or do you assume a global validation set across which the metrics are basically computed?
Yeah, it's a great question. So during model development, you ideally want to have some way of calculating how well you're generalizing, and we're going to talk more about that towards the middle of the talk. But people can kind of do either. So if you do happen to have some data in a centralized setting, which you can use for validation, which is a proxy for the thing you care about, then you can use that. Or you can also split out some of the data on the clients, maybe take 80% of the client's data for training and 20% for that validation. So similar to normal machine learning, you can hold out data in that way.
All right, okay.
Good question. Cool. So just an example to make this a little bit more concrete for the medical AI setting. Imagine the following setting, which we call cross-silo FL instead of cross-device FL, where different hospitals are different silos. The clients in this case are hospitals. Hospitals have maybe tight regulatory concerns around data sharing and privacy. They can't share the raw data. Each hospital has many chest x-rays and diagnoses about whether the chest x-ray demonstrates pneumonia or not. Applying FL enables us to learn a classifier to predict pneumonia from the chest x-rays, and it's trained using the real in distribution data. So not using some public data set, which might not be specific to the hospital, but trained specifically, for example, for the demographics of the hospital. Just some characteristics of federated learning to give you a better color of what the setting typically looks like. So typically clients are non-identically distributed or non-IAD. So what this means is that each client or patient or hospital, for example, will have a different data distribution that their data is coming from, as opposed to the normal kind of machine learning empirical risk minimization setup where you have one general distribution and then you're sampling from that one general distribution. Communication is also expensive. So sending the model weights back and forth is generally something to be minimized because it kind of slows down training and can be difficult. Clients can also be unavailable. And so especially in the kind of the cross-device setting where you might have millions or billions of devices that you are training with, a lot of these devices might not be available at any given time. And so you can't just assume that you can train on all of them at any given round. And even if you could, if it's a billion or a million devices, then you can't do that realistically anyway. And there might also be compute and memory limitations on client devices. So the devices themselves, whether they're devices in a hospital or people's mobile phones, have limitations, and those limitations may vary across devices. And so that's another challenge we face. So I've been referring to two main settings, cross-device and cross-silo. There are other settings that we might care about, but this talk will focus on these two. So cross-device refers to the setting where you might have a very large number of usually mobile devices, potentially millions or billions. And Google has done some work in this scenario. And you sample a small percentage of those clients at any given round for training, and then you have to deal with things like compute and memory limitations and unreliable availability. In the cross-silo setting, some of those limitations are a little bit relaxed, but you still have to deal with them a bit. This might be a setting where you have, like, for example, 10 hospitals that are kind of collaborating together to train a model. Some of these aspects of training are still there, though, so communication might still be expensive, for example. Cool. Hopefully that was a decent overview of federated learning. Does anyone have any questions? I want to stop in case there's confusion. Okay, cool. Let's move on to talking about generalization and federated learning, and then we'll talk about what that has to do with medical AI. So typically we care about generalization when we talk about machine learning. We want to make sure that the models that we're training are not overfitting and they can generalize to new settings. As we mentioned before, clients can kind of be thought of as having their own local data distributions. And what we care about in this setting is the performance on those local data distributions. Like the final thing we care about is like, how well will it do on this patient, or how well will it do in this hospital? And we don't care about just the aggregated data, right? That's not quite the thing we care about. So how do we define generalization in this setting? So I'll be talking about work that myself and my team conducted over the last year. That's now culminating in the ICLR paper. So we're building on the insight that FL data, federated learning data, can be thought of as being sampled from a distribution of distributions. So at the highest level, you have a population distribution from which we sample client distributions. So in the cross-device FL setting, you're sampling devices to use for training on any given round. And the lower distributions are the client distributions from which we sample the final data that we care about. So if you look at this example on the right, this is like an MNIST style data set where you have two different clients with two different columns of data. You can see they have different handwriting styles a bit. You can see, like, for example, one of them writes sixes more boldly, things like that. And so we want to make sure that we're kind of capturing this in our notion of generalization. And one thing I want to highlight is that this isn't really only relevant in federated learning. This is relevant in any scenario where you have data and it can kind of be partitioned into different users, patients, hospitals, anything like that. And the assumption is that these users, patients, hospitals have different distributions of data. So I'll talk more about this later. Okay, so now how do we take our idea of generalization gaps, which we have in regular machine learning, the empirical risk minimization setup, for those familiar, and how do we extend that to federated learning? So in centralized learning, we usually care about one generalization gap, what we can call the out-of-sample gap. So this is the gap between your kind of empirical risk on whatever data set you care about and the expected risk from the distribution that you're sampling from. And in federated learning, we actually care about two different generalization gaps. So we have that out-of-sample gap, which is the difference between performance on seen examples and unseen examples on the clients that you've seen before. And we also have this idea of a participation gap. So as a reminder, especially in the cross-device FL setting, you have this scenario where you have potentially millions or billions of clients, and you can only sample a very small number of them each round, maybe hundreds, and you might perform like 1,000 rounds of training. So you'll never actually reach full participation in your federated training. And even in the cross-silo setting, even if you have 10 hospitals, you still care about, if you were to add another hospital, or if you were to evaluate this in another hospital, how well would you perform? And so the participation gap is still relevant there. So the participation gap means difference in performance on unseen examples between seen and unseen clients. So I want to kind of explain this a little bit more with by talking about how we can empirically measure this kind of thing. So one way to kind of empirically measure this kind of thing is shown on the right. So on the right, we have a bunch of different columns of data. Each of these columns belongs to a different client in a federated learning setting. What we can do is kind of split this up into three different partitions. And we can also, so this is kind of getting to the question around like how do you do validation data in federated learning. So one thing you can do is you can have this participating training client data, which belongs to clients who do participate in training, and also their data is specifically used for training. You can also have participating validation client data. So this belongs to clients who you see during training, but we don't use their data for training. And lastly, we have unparticipating client data. So these clients are completely held out. So their distributions are completely held out. And so this enables kind of measuring these gaps in settings where data comes from a distribution of distributions, both in federated learning and centralized settings. So I'm going to explain this a little bit more, but I also want to stop for questions because this is a lot.
May I ask a quick question about participation gap? So in terms of multiple unparticipated clients, do you usually look at the worst case scenario, or is it more like an average of all the participation gaps?
Yeah, that's a really great question. We'll kind of briefly touch on this, but we actually don't really talk about this in this presentation. The paper has more on this. I think the best way to really think about this is as a distribution of participation gaps. So instead of just computing the average participation gap, think about like what are the percentiles of participation gaps look like? So our tail clients, for example, exhibiting a higher participation gap than like the clients who are kind of more in distribution. So that's something we tentatively observed in our experiments, and we have some results on that in the paper, but I don't talk too much about that in these slides.
Mm-hmm. Okay.
Next slides, I'll report average, but yeah, we did look at that as well.
Mm-hmm.
Good question.
I have a follow-up question. So I think it's a great way that you've kind of like differentiated the out of sample versus participation gaps. I'm wondering if you have like new semantic data in your distributions that have never been seen during training. Would that be like which of these gaps would it actually correspond to? Or if there's a new category, which, let's say like you have a completely new class that one of the participating clients has, which has not been seen during training. Wanted to know your thoughts on that.
Yeah, it's a great question. So it really depends on how we kind of formulate the problem. So if for example, we kind of model the client distribution as having that class, but we just didn't have to not sample that, then that would be part of the participation gap. So if there is a change in that kind of population distribution, so for example, if new clients come in and they have a new class now, and that I think is another problem, which is harder to deal with. So I think that is kind of analogous to the problem of out of detection distribution, machine learning in general. And that's kind of an unsolved problem as well, right? Like, how do you, if you have no other information about like
Exactly.
the other data is coming from, how do you solve that? So I think we'll face a similar challenge here.
Got it. Cool. Thanks.
Cool. Any other questions? Cool. I want to talk also about what the participation gap actually gives us. Why not just care about the out of sample gap like we do in normal machine learning? So one thing it gives us a kind of quantity kind of intrinsic to the data set around client diversity. And so if you observe a participation gap or a greater participation gap, that's a good way to know that your data is diverse and that training on more clients is a useful thing to do. The second thing is that similar to how measuring generalization gaps in centralized learning lets you know if you're overfitting or not, this also lets you measure whether you're or not you're overfitting on the population distribution. So if you're in the scenario where you're not seeing an entire class, even though it's in your population distribution, then that'll basically show up in your participation gap as long as you have enough data to accurately measure that. It also quantifies robustness to new clients. So if you were to add a new client that was sampled from the same meta distribution, then the participation gap tells you, or the same population distribution, and the participation gap tells you how likely you are to perform well on that. So for example, if you have 10 hospitals and they're sampled from some hospital distribution, you add an 11th hospital, the participation gap should tell you, if you're measuring it correctly and you have enough samples to be able to measure it, that how well you can perform in that 11th hospital. And lastly, it also provides an incentive for clients to participate, which might be most relevant in the cross-silo setting. So if there is this participation gap between participating and unparticipating clients, then it's a good reason for a hospital to participate in this kind of collaborative training scheme because it can improve its performance basically by participating. So prior works usually either ignore the participation gap or fail to kind of specifically measure it versus other generalization gaps. So does this so-called participation gap actually exist? So this is one of the first questions we want to investigate in our work. So we set up federated training for 4 vision and 2 text-based tasks. So 4 vision tasks where we're doing some kind of classification, and for the text-based tasks, we're doing next character prediction or next word prediction. So the participation gap is the difference in metrics between the participating validation and unparticipating data. So on the top right, we have a little bit of a color guide at the top right, but also if you compare the orange line and the purple line in all of these plots, there seems to be a bit of a difference. To get into C's point, I think in other experiments, we also notice the participation gap. These are average results. This can also be worse for tail clients, depending on the scenario.
I have a quick question here. So when you're designing these experiments with toy data sets, for example, in MNIST, the unparticipating clients should technically have very similar distributions to the participating clients because they're all from the similar data set. So how do you deal with like how does this generalize to real world situations where the unparticipating clients might have like really different distributions?
Yeah, it's a good question. So the MNIST scenario is definitely very simplified for sure. The Shakespeare and Stack Overflow data sets, Stack Overflow data set in particular is generated at much larger scale than some of the other data sets. And it's generated from real world question and answer data on the site Stack Overflow and partitioned by user. And still there, we kind of observe that kind of difference as well. I think this again has to do with your question of like, what if it's really different? Can we have any guarantees? I think no, it's not really a cleanly solvable problem. But if we do have this assumption that there is a meta distribution and we're sampling from it, then I think it becomes tractable.
And I thought it's very interesting that even for MNIST, you see this difference between participating and non-participating clients. I would have assumed it would not be that much compared to like Shakespeare or Stack Overflow, where there is like a considerable difference.
Yeah, absolutely. And we're going to talk more about the scenarios in which this shows up and when it doesn't show up in the next few slides as well.
Thanks.
Cool. Any other questions? Cool. Okay, I'm going to talk now about different ways of kind of making federated data sets. So when you're doing data sets in federated learning, you also have to get information about how the data is partitioned into clients. And typically these clients are non-identically distributed. So in addition to the data itself, you have to have, for each example, a label or like some kind of annotation around which client it belongs to. And so a common thing to do is for federated models to use centralized data sets without these natural client partitions to be able to compare with centralized results. So these data sets are typically synthetically partitioned. So they're natural data sets in the sense that they're not trained with GANs or something like that, but they're synthetically partitioned into different clients to ensure heterogeneity across clients, often using a scheme called label-based partitioning. So we have a reference below, but the high-level idea of this label-based partitioning scheme is you are sampling from, it does this kind of distribution of distributions assumption where you have usually a Dirichlet distribution at the top, and from that you get a multinomial distribution over labels for each of the clients. So if you're doing like a dog-cat classifier, like some people have more dogs than cats, basically is the thing that's kind of encoding. And then from there, you kind of randomly sample dogs and cats uniformly from the data set according to the multinomial probabilities. Does that make sense? The details of that aren't really super important. I just want to give some color in case someone was interested. So one thing we noticed actually is that the generalization behavior differs for these synthetic data sets. So if we look at MNIST training with natural partitioning on the left, so this is partitioned by the writer, so this is a partition basically on people's handwriting, versus the label-based partitioning scheme that I just mentioned, there's a significant difference in the size of the participation gap between natural and label-based partitioning. Also, if we look at the right plot, at the top, we have naturally partitioned MNIST, and at the bottom, we have label-based partitioned MNIST. We t-SNE project a bunch of different examples from the data set. And in blue, so that's the gray points. And then in the blue points, we project the points for a single client. You can see in the top picture, those points are a lot more clustered. So we plot 100 points. So those points are a lot more clustered. And on the bottom, those points are kind of spread out throughout the data set. And so this kind of makes sense given what we know about the data set. We are basically, or about the label-based synthesis scheme. Whenever we are sampling for a given label, we sample uniformly over the whole data set. But this doesn't ensure things like, for example, making sure people have consistent handwriting across all their examples. And so it might be the case, and this was our hypothesis, that when we do label-based partitioning, you are basically ending up with clients who have a diversity of handwriting, for example, for MNIST. And then there's not going to be that much of a participation gap because it's kind of closer to being IID, if that makes sense. Any questions?
One just a quick question. So in these clusters, do the clusters correspond to like different classes, or do they actually correspond to like different clients? Just curious to see how are they clustering.
Yeah, they correspond to different labels, because I think labels are definitely a bigger source of heterogeneity than differences within those labels, if that makes sense. So handwriting is a smaller difference than, like the difference between a 6.
Makes sense, yeah.
Yeah, and it should be roughly 10 of those kind of clusters, so that hopefully makes sense. Cool. So one thing we proposed in this work was a semantic partitioning scheme to better preserve generalization behavior in the setting where you have a centralized data set and you want to be able to kind of partition it into heterogeneous data that kind of makes sense. So the rough idea of this algorithm, feel free to check out the paper if you're more interested in the details, is within each label, cluster the examples within each label using a pre-trained image encoder. So take that pre-trained image encoder, encode all your images. It can be trained on ImageNet or whatever. Encode all your images and then cluster them using a Gaussian mixture model. So do this separately for each label in your data set. So this is for classification data sets. So for like 0, make like, for example, 10 clusters of what 0 looks like across all the different examples in your data set. And the goal of this is to make sure that there's intra-client, within client, and within label consistency in examples. So when we're going to sample from this eventually, we're going to sample from those individual clusters, and we're going to make sure that we're getting basically zeros with similar handwriting for a given client, if that makes sense. The next step is basically matching clusters across labels. So one problem with, if we just did the first thing, one problem with this is that the handwriting would differ across like 0 and 1 and 2 and so on. So the second step is basically there to make sure that it's consistent across labels. And so basically we match the clusters across labels based on the KL divergence between Gaussian clusters. If you're unfamiliar with that, the details aren't super important, but it's a measure of distribution distance between the different clusters that we've learned from step 1. And so you can see an example of this result on the right. So on the right, you have a client who's kind of learned to, or like an example of a client who many of their digits are both written similarly within a digit and also cross digits. For example, on the right, the handwriting is a little bit more bold, for example. Any questions?
Could you explain the second one? I think that's super interesting because like even with the example on the right, you have 6 different clusters for each of the labels. But how do you, I mean, the bold versus the not bold is pretty intuitive, but there might be other variances as well. So how does your KL divergence metric actually get those corresponding clusters?
Yeah, it makes sense. So a lot of these things basically are coming out of the pre-trained image encoder. So if the pre-trained image encoder is not being able to kind of encode differences, for example, like the difference between a 7 with a little mark in it, I think it's common in European countries or something, and that the regular 7. If the model can't encode that, then this won't work for sure. So basically, it's encoded in that kind of representation from the image encoder, and then hopefully, what step 1 will do is, for example, learn a different cluster for the 7s with the little mark in it, and then in the end, when we're trying to match clusters across labels, then the final result is that like a given client who has a given clusters that are matched across the different labels will have either 7 or not 7, and also the things that are client closest to it in the embedding space that kind of co-occur with it the most.
I see. Maybe I don't want to take up too much of the time here, but just a quick question. Maybe you would prefer to answer it later in the discussion, but do we really need step 2? Like if you just had, so let's say 60 different clusters because you have 6 per each label. If you just sample from them uniformly, making sure that you have enough samples from each label, would that still be enough, or does this intra-client, inter-label consistency improve something that, like, does it add additional information?
Yeah, it's a good question. Another way to think about this is actually that it's removing information. So we actually measure the entropy before and after this process of a given client's data set. And the kind of intuition here is that if you have, it's not really as clear with MNIST, and I'll show an example of this in a couple of slides. But if you have more variability in what a client's distribution looks like, so maybe I can just show the example now. As an example, this client 11 has a bunch of pictures with the white background, right? And that is potentially maybe somewhat realistic, and maybe roots in this data set as well, where they have a white background or something like that, right? And that can be kind of realistic, right? You can imagine somebody taking more photos with a white background than other people and stuff like that. And if you have this scenario where it's complete diversity across labels, then it becomes easier for the model to be able to learn from that diversity, if that makes sense. And so the data is a little bit less non-ID than it would otherwise be. And so we would observe less of a participation gap.
I see. So it's almost like you're guiding the model to understand certain like obvious kind of differences rather than like making it completely random for it to learn. Is my intuition correct? Or
yeah, absolutely. And the goal here is not just to make it harder for the model, but also to make it more realistic, closer to the generalization behavior.
Got it. Okay, thanks.
Yeah. Cool. Yeah. Any other questions on this rough idea? Okay, cool. Next, I will show some results. So this is on CFAR 10 and 100. So on the first and third plots, you can see the label-based partitioning results. You see there's not much of a participation gap there. And then on the second and fourth results, you see that there's a bit more of a participation gap when we do semantic partitioning. So we're observing more significant participation gaps there. So this is just an example of the result on MNIST. So you can see, for example, the first client has very bold letters, both within and across labels. And some of the other clients differ in other ways. Similarly for CFAR, as we showed, you can see differences in backgrounds and things like that. Okay, cool. Any questions? Okay, now let me talk more about what this has to do with generalization in medical AI, which is definitely a very important issue in medical AI right now. So as many of you folks know, I think generalization remains a major challenge in medical AI. So we know that deep learning has resulted in a lot of advances in neural models, especially with CNNs and transformers and so on, especially in vision. And so this ChexNet work out of Stanford definitely played a major role in a lot of that. But clinical applications are still pretty limited for this kind of narrow kind of classification systems. In part, I think due to the challenge of generalization to diverse patient populations. So a lot of these times when you train, I think for chest X-rays, we actually do have a good number of data sets for especially for other kind of scenarios. You train on one data set, you change the lighting conditions or change the hospital or change the machine that's used to kind of do the imaging. And then suddenly the results that you get don't really generalize well to that different scenario. And so I think this is probably one of the biggest reasons that the impact of a lot of this work has been kind of limited so far. So one thing I want to suggest is that medical data can be thought of as coming from a distribution of distributions as well, whether or not we're talking about centralized or federated learning. So medical data originates from hospitals or individual patients. What we care about is performance of these final clients and the distribution of that performance, not just like some performance on some aggregated data. And again, this is not really specific to federated learning at all. Everything we've said so far is actually general to centralized learning as well. So for example, we could do the three-way split in centralized learning as well, and we did do that in the paper and showed some results for that as well. Just to talk more about this point about hospitals and patients having their own local distributions. So for hospitals serve different demographics like age, sex, race, location, underlying conditions. So you can think of them as having different data generating functions. And so this kind of local distribution idea seems pretty useful there. And even for patients are obviously highly multidimensional, multifaceted, and can generate different but also related information over time. So for example, for heart rate, you can measure someone's heart rate many times. It's going to be different each time, but there's still some information that you're getting from that. It's still being sampled from something. Any questions about this framing? So I think one thing I want to argue is that treating hospitals or patients or clients in any of these kind of scenarios as identically distributed and aggregating into one data set can sometimes be throwing away information that we could use to measure and prove generalization to new hospitals and patients. Especially the measuring point, I think I'm gonna talk more about in the next few slides. So can we extend our three-way split idea for medical data? So I think we can. So basically, we can think about this picture, which I've kind of blown up a little bit. So we have participating training, participating validation, and unparticipating clients. I'm going to use the word clients, but clients here refers to either patients or hospitals in this scenario. Each column contains examples per patient, like in the previous pictures. So we can use participating training to mean seen examples from seen patients in hospitals. So these are the examples that we use for training. We can use participating validation as unseen examples from seen patients or seen hospitals. And lastly, the unparticipating can be completely held out stuff. So held out patients, held out hospitals, and held out examples that were not used in training. So what do we get from this? So now we can measure the participation gap in both centralized and federated medical AI settings using the difference between this unparticipating and participating validation metrics. So what does this give us? A lot of the same things that we talked about before, but now specific for the medical AI setting. So now we have an idea of expected performance on unseen patients in hospitals, especially if we have a diverse kind of data set. We can measure diversity of data coming in from patients and hospitals. This gives us a way of telling how well our models are kind of adapting to that diversity. We can measure overfitting on specific patients and hospitals, which has obviously been an issue in medical AI. And we also have this valuable tool for iterating on model deployment. So the same way, knowing the difference between your kind of performance on validation and train in normal centralized settings is kind of a useful way of telling whether you should do L2 regularization or things like that. This is another such valuable tool. Any questions?
I have a quick question. I think this is super interesting, especially that like there is a lot of heterogeneity within a data set also, like you pointed out in medical data sets. And so treating them, like basically finding out the subgroups that have some similarities might actually boost your performance really well. So I'm curious if to know your thoughts about, so is the idea here that you divide them into subgroups that have, similar cluster, like they cluster based on some characteristics? And do you do a federated learning kind of a thing, or do you do a different kind of training? Like, does it have benefit to actually choose a random subset of clients and do the federated averaging kind of a scenario? Or is it even better that now that you have these clusters, can you do a different kind of sampling in your regular centralized training?
Yeah, there's a bunch of interesting questions there. So, first question on the data sets, like how do you figure out how to cluster these different data sets?
Mm-hmm.
The thing is it for it to come naturally from like different hospitals or different patients, and you use that as kind of the clustering or the partition across different things. So that would be the ideal thing. And then the question is, how does this affect our training, or should we do training differently, and how should we do measuring differently? So right now I'm just talking about measurement. So measurement of generalization right now. In terms of the training question, this is applicable even if we're doing centralized training. So this measurement question. So you can do normal centralized training where you put all the data together and then you train it. And then for this part of it, you kind of separate things and make sure you evaluate on the different kind of splits, if that makes sense.
I see.
And then, but the later part we'll talk more about like whether there's some utility of federated training for this specific purpose. So like, do we actually get something from leveraging this kind of distributions assumption in doing training? So I'll give you. So we're going to talk more about that with a specific algorithm. But even for federated averaging in particular, there are papers that argue that when you're doing federated averaging, you're doing this kind of meta learning thing. If you're familiar with meta learning, where you are kind of learning to quickly adapt to new kind of scenarios. So you're learning to quickly adapt to new patients and new hospitals. So that like if you want to fine tune that model, you're actually explicitly training for that. So that's an argument for doing that kind of thing. But there are also centralized meta learning algorithms as well. But it turns out federated averaging by accident is doing something very similar to a meta learning algorithm, a first order meta learning algorithm called Reptile. So I can send everyone references on that if people are interested.
Awesome. Yeah, thanks. And we in our group kind of with our collaborators, we've kind of seen this trend where we see this hidden stratification within a lot of groups. And so like even without clustering just by users or hospitals, we see that like some of the labels themselves have some hierarchy, and so they cluster based on that. So that might also be something interesting for you to like think about, like doing the clustering for identifying like something apart from just users or hospitals. So
yeah, absolutely. Yeah, there are previous works also trying to do this hierarchical clustering type idea as well. And in general, we've been talking about like distribution of distributions, but there could be even more levels than that, right? Like you can think about the hospital level, then the patient level. So you can think about the hospital distribution, then the hospital level, then the patient level. So there could be multiple distributions, multiple levels of distributions, even beyond. Although I think 2 might be the point where it starts to get awkward in terms of benefits. But maybe that remains to be seen.
Nice. Yeah, I think this is a great formulation. Thank you.
Yeah. Cool. Good question. Cool. Okay, so some takeaways from this section. I want to basically argue that medical data comes from a distribution of distributions, whether or not we treat it that way. We can use this to measure and improve generalization, even if all we do is modify our tools that we use to measure generalization and use that to kind of iterate on model development. The 3-way split in particular is generally useful for doing this and measuring overfitting and things like that. And lastly, in federated settings where we don't have kind of already partitioned data, we can use semantic partitioning or maybe hierarchical versions of that to ensure kind of more realistic generalization behavior in these settings. Cool. In the next part of my talk, I will talk about an algorithm. So far we've been talking mostly about what generalization is, how it applies to medical AI, but not really talking about how we can actually improve it. And so now I'll talk more about an algorithm that aims to improve it in this kind of distribution setting, leveraging that fact. So a little bit of recap. So these algorithms tend to kind of aim to handle things like client distribution heterogeneity, like differences in kind of the distributions across clients, communication constraints, and also unreliable availability. Usually, models are either trained globally across users, so you learn a single global model across all the different clients that's shown on the right. So the different clients have different colors because they're a little heterogeneous, and the global models may be some kind of mixture of all the individual models. Or you can train on individual data only. This isn't doing federated learning at all. This is completely personalized to that client or that user or that hospital, but you don't have enough data typically, and that's kind of part of the motivation for federated learning. So can we do better than this? How can we leverage this kind of distribution setting to do better? How can we get the benefits of both this kind of federated training, which gives you more data, and also personalization to local distributions while preserving privacy? And so to give you a preview, federated reconstruction is basically a scalable framework for training these models, which are partially global and partially local, in a way that kind of works in real world FL settings. So now kind of step back, we're going to talk about a specific use case that we kind of examined in the paper, and then I'll connect it back to medical AI and what that has to do with it later on. So one use case that we examined is a kind of classic machine learning setting of collaborative filtering. So the goal here is to combine preferences across users to better understand their behaviors. So an example is movie recommendation. So you have you users, I movies. Each user rates some movies from 1 to 5, but they don't rate all the movies because there's a lot more movies than they can individually rate. And so you can imagine this as a kind of sparse U by I matrix, where some of the entries are there, some of the entries are missing, and our goal is to predict missing entries. Any questions on this setting? So the kind of classic approach for dealing with the setting is factorize that rating matrix R, which we showed on the previous slide. So this is that U by I matrix, which is sparse and has the ratings, into two matrices, P and Q, which contain basically embeddings for the users and movies that you care about. And these users and movies are predictive of whether or not someone will enjoy a movie, even if that rating wasn't in the original matrix R. So you're learning this, you're factorizing, you're getting this P and Q. The rating is a dot product of these user item embeddings corresponding to that row and column, respectively. So the typical or this most simple training objective for this is minimizing mean squared error on observed preferences. So given a bunch of observed preferences, the ratings for specific movies, you are learning P and Q using SGD, for example, to minimize those mean squared errors, if that makes sense. So there are modifications of this, and we ended up modifying it as well. But this is like the simplest kind of setting. So now how do we bring this kind of matrix factorization setting to FL? By the way, the reason we care about the setting, which I will talk more about later, is this is relevant anytime we have client-specific embedding. So if we have an embedding for a hospital or we have an embedding for a patient, we don't want to be sending that to everyone, sending that to the server back and forth. So the naive approach of sending these kinds of embeddings back and forth doesn't preserve privacy, even with like advanced privacy preserving technologies like differential privacy or secure aggregation. I won't talk too much about these technologies, but they typically can improve privacy in these kinds of settings. But in this case, it doesn't really work. So the intuition is, can we try to keep these user embeddings local instead of sending them back and forth to the server the way we do typically in federated averaging? So some previous work on this has explored what we call stateful partially local algorithms. So partially local means part of the model is local. Stateful means clients have to maintain state, like their previous parameters, their previous user embeddings across different rounds. So this is going to be problematic in cross-device FL, and I'll talk more about this in the next slide. So the two previous works that are most relevant here also kind of don't quite scale to the real world cross-device setting because they have limitations like assuming all clients are available at all times, or not really proposing a way to perform inference on clients that were not seen during training, which in our scenarios at Google ended up being most clients. So what are the problems with statefulness, especially in cross-device FL scenarios? So the total number of clients that you really care about in these cross-device FL scenarios can easily range, can easily be in the hundreds of millions, depending on kind of the setting that you care about. So the number of the clients that you want to perform inference on with your final model could be in the hundreds of millions. Your number of training clients could be like 100,000, or sorry, like maybe half of that, like 50 million or 10 million or something like that. Then the clients reached in practice by your training, if you're sampling 100 clients per round, doing that 1,000 times, for example, it could easily be just like 100,000. So you're sampling a very small percentage of the clients that you care about. And whenever you do sample those clients, you're only going to sample them probably once. And so we can't really rely on there being a state being available across rounds, because if we sample someone, we're not really going to sample them again. So it doesn't really matter whether we ask them to remember some user embeddings from the previous round. Even if we do resample them, their state might become stale because we might not have sampled them in a long time. And so that can cause performance degradation as well. Lastly, we're just not realistically going to reach all inference clients. So some users will not have user embeddings if we use this kind of approach, where we remember the user embeddings. So in our setting specifically, 99% of users plus would not be able to use the model if we did a stateful approach. And so I won't talk too much about the details of this approach, but I will kind of give an outline of this, specifically applied to matrix factorization. But what we do is on the server, we have a Q matrix, which is the item embeddings. We send that to the individual clients who are selected for training. We perform what we call reconstruction, which is local SGD with Q frozen to reconstruct their personal user embedding. Basically, the intuition is that we can reconstruct the user embedding on the fly whenever we need it. And then we update Q based on that frozen user embedding. So we're doing 2 stages of SGD in this scenario, and then we aggregate updates across Q by doing things like averaging, similar to federated averaging. This is a lot of information. Any questions? So the intuition here is, instead of remembering the user embedding across rounds, we are reconstructing it on the fly whenever we need it. So this is a kind of generalized algorithm, not specific to matrix factorization. So in the previous slide, whenever I talked about Q and P, you could replace Q with global variables, you could replace P with local variables, and all the same things would be interesting to explore. So any federated learning model can be partitioned, and we implemented general libraries in TensorFlow Federated that lets anybody kind of try this with their model. So when can this be useful? When you have models with user-specific parameters like matrix factorization, or any models with user embedding. So you can imagine, for example, a chest X-ray classifier that has a hospital embedding. So for that hospital, it takes in that embedding and that basically personalizes the behavior of that chest X-ray classifier to that hospital. So you can also talk about models with trained on heterogeneous clients. So basically any setting where you have distribution of distributions. Also communication limited settings, basically because you're reducing the amount of communication you're doing by not communicating these local parameters. So I'll kind of give an overview of our matrix factorization results. So federated reconstruction actually outperforms centralized and federated averaging training by leveraging this distribution of distributions idea. And it avoids centralizing privacy sensitive parameters as well. So it gets both an improvement in utility and improvement in privacy. There's also connection to meta learning, which I kind of alluded to earlier. We're basically training so that we are getting improved performance on unseen clients. We're learning to learn on unseen clients. Another way of saying this is we're training global parameters that lead to fast and accurate reconstruction of local parameters for unseen clients. And in practice, what we observe is that even one gradient descent step can yield successful reconstruction, even if you have 1 million local parameters that you're kind of reconstructing. So you can see on the right, we have an ablation where we vary the number of reconstruction steps. More details on that on the paper if you guys are interested. We also evaluated our next word prediction and Stack Overflow, similar data set as we talked about before. This is a large scale, pretty realistic data set. We personalize the language model's input layer in the same way that we could personalize the input layer of like a chest X-ray classifier. In this case, we attain accuracy comparable to other methods in personalization and significantly higher than kind of the baseline FedYogi, which is a variation on federated averaging. Again, by leveraging this distribution of distribution setting and still beating other or performing comparably on other versus other kind of personalization techniques while also communicating less. We ended up deploying this to part of the motivation for this was we want to be able to kind of scale to real world cross-device FL settings. So we ended up doing this in the setting with a population of hundreds of millions, and we basically deployed federated matrix factorization and got an improvement in recommendations. So some takeaways from the talk: medical data comes from a distribution of distributions. We should use this to measure and improve generalization. The three-way split is generally useful. We can use semantic partitioning to ensure realistic generalization behavior. And from the last part of the talk, federated reconstruction could be a way of actually leveraging this distribution of distributions assumption to learn models that are more adaptable and do less communication. Any questions?
Do you have some preliminary results or like results on medical applications of your three-way partitioning and generalization work?
Yeah, nothing that's too advanced that we can present at this point. We're early in our applications of medical AI at this point.
Mm-hmm. So let's say if there are like multiple hospitals, but they are under the same like healthcare system, like same big system, would you recommend like consider them as different clients or like same clients?
Yeah, I mean, it depends on what assumptions might be most useful. So it could be if we have the hypothesis that hospitals in the same system might have a similar kind of distribution of patients, then maybe it's useful to consider it as one single client, especially if we're talking about collaborating with other kind of hospital systems. It could be useful to consider them all individually as individual hospitals across, like even across the different systems, or it could be useful to have a multi-level kind of distribution assumption. So you have a distribution of hospital systems, a distribution of hospitals within those systems, a distribution of patients within those hospitals. So that can also be a kind of an assumption that you want to take.
Makes sense. Thanks.
Cool. Yeah, so these works were joint work with the co-authors and many other collaborators as well. So I've linked the papers here. I've also linked more resources for people interested. So I can kind of briefly go describe some of these resources as well. So by the way, these slides you can get through this tiny URL link, and so you can find these links as well. So on Federated Learning, we have this AI blog post, comic book, survey papers. We have this TensorFlow federated platform, which lets you run simulations of federated behavior as well using TensorFlow. For the what do we mean by generalization FL paper, we have a link to our ICLR paper as well as experiment code. This includes evaluation on 6 tasks, the three-way split idea, the dataset synthesis. And for federated reconstruction, we have this blog post, which is a good overview of the method and the application. We have the paper. We have a TensorFlow.org tutorial walking through kind of applying this in a Colab or a Jupyter notebook. We also have some libraries and experiment code for those interested. Any last minute questions?
Okay, great. Thanks, Karan, for the amazing talk. Let's give him a round of virtual applause. And if any of the audience have questions, feel free to speak up and ask.
I can start with the questions, I guess. I thought this was a great talk. Thanks, Karan. I had a quick question about your matrix factorization for reconstruction. Do you think it's was it scalable for devices with low compute resources also to do this matrix factorization on the fly? And any thoughts about resource constraints and how it would trade off with this approach?
Yeah, absolutely. So that was definitely something that we had in mind because we were, training on real world devices there. So yeah, we had pretty strict kind of limitations on how much memory could be used and stuff like that. The training only happened when devices were idle, so you also had like unreliability in their availability and things like that. So we handled a bunch of challenges around that as well. And kind of zooming out with this reconstruction approach, you're doing this extra step of SGD to kind of reconstruct things on the fly. But you kind of have to do that anyway, regardless, right? Because you're not going to have the state in a stateful approach. And one thing that I mentioned was that in the user embedding case, the matrix factorization case, we're training actually a pretty small amount of local user embeddings, and we observed that even training with one local step with those user embeddings was giving you pretty good results. And so it seemed like it was actually just not like a huge computation cost. The biggest kind of bottleneck was more around communication, I think, realistically.
Yeah, that's pretty cool. Yeah. And the resources that you pointed us out to was also like very useful, I think. Are there any other questions from the audience? Okay, then if not, C, do you want to like do the concluding thing?
Yeah. If there is no further question, let's thank Karan again for the very interesting talk. And we will upload the video or the recording of our talk later to our YouTube channel. And feel free to reach out to us or Karan directly to his email if you have any further questions. Thank you everyone for joining us today, and see you next week.
Thank you.
Thank you.